So for part A, it asks, should the students use a long tube or a short tube to make the stopping distance d the longest? So right off the bat, it says a constant force, which means that there would be a constant acceleration. And knowing that, we can use a common form VF squared. It's assumed that it starts from rest, so VI is 0. And we're left with VF squared equals 2a delta x. Since the acceleration is constant, we cross this out. And we're left with VF squared equals 2 delta x. So this means that the distance would affect the velocity. So that means if the distance is short, then the velocity would be smaller, and vice versa. And so the delta x represents the tube length. So if we want to make the stopping distance longer, then we should go with the long tube, because the long tube would make the velocity greater. And if the velocity is greater, then that would make it so that more momentum is gained, and that would make the tube hit the ground harder and then slide a longer distance. For part B, it shows an equation that a student found in a similar experiment situation. And so it's asking, does this equation to find the stopping distance d agree with my reasoning in part A? And if it has the expected dependence, the same expected dependence as in part A. So let's go through the equation first of all. So D represents the stopping distance, F represents the force applied by the tube, the L represents the length of the tube, lowercase m represents the mass of the dart, and then all that is divided by the mass of the dart and plus the mass of the block squared times mu k and times gravity. So looking at this equation, we know right off the bat that the F is constant because it was already stated in the question. The M is also constant because it's a fixed number. And G is constant because it's gravity. And same with mu k because it's also a fixed number. And so knowing that F, M, mu k, and G are all constants, they are not actively affecting the stopping distance, which means that L is the only actively affecting factor. So this basically means that yes, it does agree with my reasoning in part A, because in part A I did say that the length of the tube affects the stopping distance because of how the length of the tube affects the velocity and affects the momentum and ultimately affects the stopping distance. So yes, the equation for D does have the expected dependence as reasoned in part A. So for part C, it's asking, should the students use a dart with a large mass or a small mass to make the dart block stopping distance D the longest? So we can first use net force equals ma. So what we know is that when the mass is small, it would result in a larger acceleration, and when the mass is large, it would result in a smaller acceleration, right? And so, using that idea, we can use the initial momentum equals final momentum, and we could do mv1 I. So it results in an elastic collision. So based off this, if the mass is smaller, that means the acceleration would be larger, which means that the velocity would be larger. And so knowing that, the initial velocity would be larger. Knowing that, we can use the common form, and final velocity is 0 because it's asking for the stopping distance. And so initial velocity would be larger, so that means that divide both sides by 2a so we can isolate for delta x, which is a stopping distance. So yeah, the larger acceleration would affect the initial velocity, and then in turn right here affect that. So that means that the larger velocity would mean a larger stopping distance. So the students should use a small mass. So for part D, it says to calculate the speed of the dart immediately after it leaves the tube. And so I'm going to approach this part by using common form. So VF squared minus VI squared equals 2a delta x. Sorry, that is an ugly delta. Alright, delta x. So we can assume that the dart starts from rest. So VI would be cancelled out. So we're left with VF squared equals 2a delta x. The VF will be the speed. So we can find acceleration by doing net force equals ma. We're given that the net force of the dart is 20 newtons, so we can just put that in. The mass of the dart is 20 grams. Oh, so we have to convert it to kilograms. So 1 gram is equal to 0.001 kilograms. So that means that that would be 0.02 kilograms. So 0.02a. So we can divide both sides by 0.02 to find the acceleration. We get 1,000 meters per second squared. So now we know the acceleration, we can just plug in everything from there. So VF squared equals 2 times 1,000, and the delta x would be the length of the tube. And I meant the length of the dart. So the length of the dart is 0.5 meters. So do that. We can multiply the whole thing. So 2 times 1,000 times 0.5 is just 1,000. VF squared, and we can square root both sides. And we get a final speed of 31.62 meters per second. So for part E, it says calculate the speed of the dart block system immediately after the collision. So, we know that this whole thing is in an elastic collision. So that means the momentum of the system, the velocity will be shared among the two masses. So we can set initial momentum equal to final momentum. So m of the mass of the mass, okay, lowercase m would represent the mass of the dart initial plus the mass of the block initial velocity of that. And then m plus m goes to be f. Okay, so okay, so we know that the mass of the dart is 0.02 kilograms, and we found earlier that the initial velocity of the dart is 31.62. And we can add it to the momentum of the block. However, we know that the velocity of the block is 0 because it starts from it's not even moving at all, right? So we can just cross that out for convenience. So now we can finish the other side. The mass of the dart is 0.02 kilograms plus the mass of the block, which is 0.03. 0.03, yeah, 3, and then final velocity. So from there, we can calculate. Hold on a second. Okay, so 0.02 times 31.62 is, my goodness, 0.6324. And then these two added are 0.05 VF. And then we can divide both sides by 0.05 so that we can isolate for the final the speed of the dart block system. So VF would equal to 12.65 meters per second. So that is a speed. So for part F, it says derive an expression for the acceleration A for the dart block system as it travels across the distance d in terms of the given variables. So I'm going to start off by doing net force F equals ma. We know that the net force of the horizontal is only F of k because it shows mu k. So we could do Fk equals ma. So now we need to look for what Fk is equal to. Fk is equal to mu k times F of n. However, we need to know what F of n is equal to before we multiply it to mu k, because we're already given mu k. Mu k was 0.14. Let me write that down real quick. Yeah, 0.14. So to find F of n, we need to consider the forces on the block. So since it's on a, like, there's like no other forces acting on it, like any outside, like any like, yeah, other forces acting on it, that means that F of n would equal to F of g. So yeah, you can see the force F of n is equal to F of g. So, and we know that Fg is equal to m times g. So knowing that, we can find the mg, we can calculate mg to find f of n and multiply that to mu k to find f of k. However, the question says to derive an expression for the acceleration of the dart block system. So that means that we have to account for both of the masses of the dart and of the of the block. So m would be m, lowercase m for dart, the mass of the dart, and then plus uppercase m, which is the mass of the block, g. So adding all of this together, we can create an expression for the acceleration. So Fk equals mu k times m plus mg. Yeah. And this can get a little confusing, so we can like put the parentheses like that. And then we can go to the original net force thingy formula. And from there we can plug it in. So mu k times m plus m g equals ma. Yeah, I think, yeah. And then we can multiply, we can divide both sides by m to isolate for a. But again, we have to consider that the mass is basically the mass of the dart and the block added together. So it would be mu k times m plus m g equals a. Oh wait, divided by m plus m equals a. And these cancel out, so we're left with mu k times g equals a. And that is our expression. So for part G, it says using conservation of energy, calculate the speed of the dart block system in the instant leaves the table. So conservation energy is initial mechanical energy equals final mechanical energy. And basically, we know that there would only be kinetic energy and energy loss because there's no potential energy because the whole system is moving strictly in the horizontal direction, and so there's no change in y. So that means that there will only be kinetic energy. And then there's also energy loss because of the mu k, which contributes to the friction. So, yeah. So KEI is 1/2 mv squared minus loss, which is work done by friction. So that's net force F times delta x. So for the net force of the mass, for the dart block system, it's basically just Fk, because that's the only force that's acting on it. And so Fk is calculated by mu k times Fn, and Fn is basically equal to F of g because F of g is the only force is the only other force that's acting on the mass block in the vertical axis. So therefore F of n is equal to F of g. And F of g is typically, or it's always m times g. So since it's referring to the entire dart block system, we have to account for both of the masses. So it'd be lowercase m plus uppercase m, which is the mass of the block, and the lowercase m is the mass of the dart, times g. From there, we can calculate the F of n. So the mass of the dart is 0.02 kilograms, and the mass of the block is 0.03 kilograms, times 9.8, which is the gravity. So 0.05 times 9.8 is 0.49 newtons. And so that's F of n. Now we can multiply that by the mu k, which is 0.14. So 0.14 times 0.49 is 0.0686. And so now we know that F of k is equal to 0.0686 newtons. Now we can multiply this by the distance, which is 0.5 meters. 0.5 meters. So we get 0.0343 newtons for the E lost. Now we can go back to the kinetic energy, which is 1/2 mvi squared. Again, we need to account for all the masses, so m plus m. So that'd be like that. So 0.05 divided by 2 is 0.025 vi squared. We can like move this up here so it's cleaner. So 0.025 minus v, oh sorry, not minus, what the hell? Vi squared equals, oh my goodness, minus 0.0343. And then we could divide vi squared to the other side to get 0.0. Okay, so 0.0. Okay, so 0.0343 minus 0.025 is 0.0093. After this, we square root both sides to find the speed. Square root of 0.0093 is 0.096 meters per second. So for part H, it says how far horizontally x will the dart block system travel before striking the ground. So I'm going to use the displacement formula. So delta x equals VIT plus 1/2 AT squared. There's no acceleration on the horizontal axis because it said, there's no acceleration. Because it's constant. So we're left with delta x equals VIT. So now we want to find the time. We know that the initial velocity was 0.096. And then we need to find time, right? So for time, we can use displacement in the y. So it'd be VI t, that is t plus. So we know that the initial velocity for the y is 0 because it is not moving in the, there's no like, wait, hold on. So VIY would basically be VI sine theta, right? But there's no like angle. So sine 0, that'd be sine times 0. Wait, sine theta 0. Theta equal 0. And so that means the whole thing would be 0 because sine theta 0 is equal to 0. So that cancels out. So we're left with 1/2 g times time squared equals delta y. We're given that the height is 10 meters and then gravity is 9.8 time. So this would be 4.9 t10, and then we divide both sides by 4.9 to isolate for t squared. 10 divided by 4.9 is 2.04. Square root both sides to find the time. We get 1.43 seconds. So now we can plug it in the original. So it'd be 0.096 times 1.43. So 1.43 times 0.096 is 0.137 meters. Yeah, why does that not make sense? Yeah, 0.1. Okay, 0.137 meters is how far it'll travel, I believe.